Hello, guys. In this video, I will introduce the solution for LeetCode weekly contest 346. And there are 4 problems in this computation with difficulty 3, 4, 5, and 6. And now we go to check the first problem at first. So this problem is we give a string only consists only of uppercase English letters, and we want to remove. So we can remove substrings of AB or CD from math, and our goal is to return the minimum possible length of resulting string that you can obtain. Like for example, for this string, right? So if we remove any substring of AB or CD, then the lefted characters can construct a new substring of AB or CD that we can remove further. So for this problem, because these characters' position cannot be changed, right? So what we should do is we just remove all of the substrings A, B, or C, D, and after we remove any of the characters, we go to check whether there is new substrings of A, B, or C, D, and if there is a new substring of A, B, or C, D, we just remove them. So for this one, we can just make use of stack. And first of all, we push the first character into stack, and then we iterate each of the characters in the string, and then we always check whether current character with the character on top of the stack, whether they construct a substring AB or CD. If they constructed AB or CD, we just record how many characters we removed here, and then we also pop the first characters from stack, and so on. So the result will be n minus removed characters. That will be the smallest length of string we can get. Now we go to the second problem. For this one, we want to build, so we also give a string that consists of lowercase English letters, and we can change any character's value in this string, and our goal is to make the final string to become a palindrome string. And if there are multiple ways to build a palindrome string, we want to get the lexicographically smallest one. And we also want to make use of minimum number of operations. For this one, actually this problem is quite direct, right? For palindrome string, actually we just check 2 characters, right? So they should on the match the position. For palindrome, one is from beginning, one is from ending. Like we check whether they are equal. If they are equal, then we just ignore them. Otherwise, such like for this one, if they are not equal, then that means we must change one of them to be the other one's value, because we want to make the final result to be lexicographically smallest. So we just select the characters, the bigger characters, and change it to be the characters with a smaller value. So the solution implementation like this. This is really a direct solution. And now we go to the third problem. For this problem, that we are given an integer n and return the punishment number of n. Punished number of n is defined like for all the integers between 1 and n, and then the decimal representation of I by I can be partitioned into contiguous substring that the sum of the integer values of this substring equals I. One sample such like n is 10, and now we can see, for example, for one integer 9, so 9 is between 1 and 10, and also 9 by 9 is 81, and 81 can be partitioned into 8 and 1, and their sum equals I, so 9 meet the requirement, and then so totally we have 3 integers meet the requirement, 1, 9, 10, and then we just calculate their power and then sum them together. So that will be the punishment number of 10. For this problem, we can make use of recursive algorithm like for each. So first of all, I iterate each integers between 1 and n and check whether they are punishment number. And first of all, so in this method, right? So first of all, I may change the power of I to be string, and then I use another method to check whether this number can meet the requirement of punished number. And in this method, that there are 4 input parameters. The first one is the string itself, and the second one is the position. So position means I already processed the characters on the left side of this position, and also this value is what I already gotten with the characters on the left side of this position, and this is the final value I want to achieve. And in this method, I go to check whether current position is already beyond the string lines. If it's beyond, then that means I already processed all of the characters now. Then I go to check whether current value equals the target value. If they are equal, then I return true, means I find a punishment number. Otherwise, I return false. And if the current position is not beyond the string lines, then I continue to process from the current position. I define a local variable named the base value. So this means what values I got in this method from the current position to a new position. And so I just iterate from current position and to the end of string. And I just calculate what is the base value I got in this currently based on the characters processed. And then I call this method again, and now I update position to be I plus 1. And the value I already got is the input value plus the value I got in this process newly, and then this value is not changed. And if I got return the result as true, okay, so this is a number meet punishment requirement, I just return true. Otherwise, I go to check the next position. And if I check all of the position and I don't get true result, then means I must return false. Okay, so this is the third problem's solution, that because n actually is small, so we can use this recursive algorithm to resolve this problem. And then now we go to the last problem. So for this problem, that we give a undirected weighted graph, and on this graph there are some edge with positive integer. So that means this weight is side and is not mutable, and there are some other edge with weight -1. So -1 means this edge's weight is mutable, that we can change this edge's weight to be any value between 1 and 2 by 10 power 9. The goal is like we are process a source vertex and a destination vertex, and we are also provided a target value. So we want to change the mutable edge's weight to be anything between 1 and 10 by 2 by 10 power 9, and also the smallest code path between source and the destination is target. And if we cannot achieve this, we return empty vector. Otherwise, we return a vector with all of the edges all of the edges weight that can meet this requirement. Okay, so for this problem, let me explain this in details of what we should do to resolve this problem. And other than use the sample in this problem, I want to draw another sample. Let me explain this problem easier. So for example, I have a graph like this. And this is our source vertex, and this is our destination vertex. And we can think about the weight like, for example, the weight like, for example, this is 4, 3, 1, 5, and this is a mutable edge. And for this one, I can set it as maybe 2, and this is 10, for example. And now, so first of all, what we do is we use Dijkstra algorithm to calculate the shortest code path with the cells. And now in the first step, so first step, we select D as cells. So now the cells vertex is D. And we calculate all of the other vertex on this graph, the shortest path length with D. And before that, we should check, we should set all of the mutable edges. Such like this is a mutable edge, right? We set its value to be infinite. So that means we want to calculate the shortest path from each vertex to destination node without using mutable edge. Okay. And now what we care about is the shortest path length between S and D. So there are 3 cases. One is bigger. So this is okay. Why? Because there are some mutable edges we don't make use, right? So even though now their smallest passes length is bigger than target, it doesn't mean we cannot find the answer if we change the mutable edges to be a smaller value, right? So this doesn't mean that we cannot find the answer. And another one, they're equal with target. So for this one means if we don't make use of mutable edge, actually we already get the shortest path between S and D equal with target. So for this one, we can construct the answer directly. We just set all of the mutable edges to be, the smallest value. The smallest value is this, right? So in that case, we can get the answer that can meet the requirement. The third path is smaller than target. So that means if we don't make use of mutable edge, the current smallest passes length between S and D is smaller than target. Okay, so in this case, we can think no matter how do we change the value of mutable edges, actually the current smallest path length can only become smaller. They cannot become bigger, right? So in that case means we cannot find the answer. Then for this one, we can just return empty vector directly. Okay, so this is the first step that we calculate. We use destination vertex as source and calculate the smallest path of each other nodes with the destination vertex. And then we make use of these 3 cases, and we can return answer for the second case and the third case. And for the first case, we need to do further check. Okay, we need further checking. Okay, now we do the second step. Second step, we make use of Dijkstra algorithm again, but this time we don't change this to be, so let me change my color. So I don't want to change this mutable edge weight to be infinite, but I change it to be 1, to be the smallest value. And also the south, now I want to use south vertex as the south node of Dijkstra algorithm. The second step is south vertex is the south vertex. Okay, so now I calculate the other node's shortest path with the south node with mutable edges with value 1. And here I also have 3 cases, right? So one is bigger. So that means that even I set the mutable edges value as 1, so this is the smallest possible value, but their smallest code path length is still bigger than target. So in this one means we can not build any, we cannot get any path that can meet the requirement. We just return empty result. And the second is equal. So for this equal, it's just like this, that we can construct answer directly. But actually, these two cases are duplicated, right? So they are same. That if equal, then we return the answer directly. And the third one is smaller. So for this one, it means that if we change some mutable edges to be 1, and now there the smallest path between south vertex and the destination vertex is smaller than target. So this is okay. And because now the mutable edges is set as 1, so if we increase this value, that we may get the path can meet our requirement. Okay, so now we just focus on this, focus on the third case here, right? So first question is, for the current smallest path, smallest length of path from south to D, does this path must include at least one mutable edge? The answer is yes, because if we don't make use any mutable edge, we already calculate in the first step, right? So the value is bigger, right? So if we don't make use of mutable edge, the smallest length of path between S and D is bigger than target, and now it's smaller. So that means the current smallest length of path must consist at least one mutable edge or even more, right? So there must be mutable edge on this path. And then what we do is we just iterate each edge on the current smallest length of path. So let's see, this is the path. We just iterate each edges on this path. And if one edge is already set with positive value, so that means we cannot change its value. We just record how long I already gone through on the current edge. On the current path. So in this case, for example, this is 2, this is 3, this is minus 1, okay? And now, for example, I from south and to this node, to this vertex, I saw their edge is not mutable, so I just record. Now I walked, so here named walked, I walked 2, okay, and also this edge weight cannot be changed, so I do nothing to change this weight value. And now I go to this edge, and also I found this edge is not mutable, so currently I update walked value to be 5. And now I find a mutable edge here. Okay, so this edge is mutable. And then what we should do? And we know that if this is 1, it may not. So it may be okay, but it may not also meet our requirement, that because we know that currently the smallest path length is smaller than target, right? So we can think about what value we can set for this mutable edge. First of all, I think you should make use of the smallest path length we calculated in the first step. So that means, first of all, we focus on these 2 vertices at the vertex of current mutable edge. And we know that in the first step, we should know this vertex smallest length with destination, right? So we calculate this as, for example, as L2, and this vertex length with destination vertex, we record this as L1. And we know that in the first step, this mutable edge is not used. So if we saw this L1 and L2, they are not infinite, then that means there must be another path, right? Another path we can reach this node from this node. So for this sample, it's 6, right? So here there is a path at 6. I can go from this node to this node. Okay. So in this case, we can think about whether I can set this edge for any weight that's bigger than 6, such like I set this edge's weight to be 7. So we found this doesn't work, because for any weight that's bigger than this value, it will make the shortest path changed, right? Because there is another path, only 6 from this node to this node, but your edge on the current smallest path with weight 7. So the smallest path the shortest path will change from this path to this path, right? So that means we must set any value that smaller or equal than L1 minus L2. Okay, so this is the first requirement. And the second requirement, that we know this from D to this node, their shortest path length is L2. And I also know that by this node, I already worked 5. So for this length, right, that means the length must be target minus work and minus L2. So this is the, so let's say if we call this as a VL like this. So this path, this edge's length must be equal or bigger than this value. Otherwise, you can think if your value is smaller than this one, right? Then you go so now if you go to this path and your worked value is 5 plus the VL you set on this edge, right? And you know, like if this VL is smaller than this value, so you can think about like the final. So if you reach the destination vertex, your worked value will be smaller than target, right? So in that case means we need to set any value that must be bigger or equal than this value. Okay, so and also another thing we must understand is for this part, right? So we must set this value for the mutable edges on this path to meet our requirement. And we must, we can do that. That's based on the first step. Like when we check the shortest path, if we don't make use of mutable from D to S, the shortest length is bigger than target, right? And now if we change their mutable edge to be 1, then their the shortest passes length is smaller than target. So that means if we adjust the mutable edges value, right, there must be some paths can meet our requirement. Okay, so that means we can go to set this passes length to be this value directly, because this value must also meet this requirement. Otherwise, it break the assumption that there must be some value we can set for the mutable edges can then make this path meet our requirement. So we can set each of the these mutable edges to be some value just like this. And another thing we should think about, if this L2 equals infinite, then what does that mean? So that means for all of the passes between destination and this node, there are mutable edges. Then in this case, we can just set these mutable edges just like 1 directly, because we know that there are also some mutable edges between destination and this node and this node. In that case, we can because this we can set very big any big value for the mutable edges later to meet the requirement. So for this one, we just set it as 1 to meet the first requirement. Okay. So this is the general idea of this problem. Then we can refer to the codes to see how this is implemented. So this is the Dijkstra algorithm. And this is go to initiate cost array used by Dijkstra. And this is for the so first of all, for the first step, if this is a mutable edge, I just change it to be a big value, infinite value, and then I use destination vertex as the source and run the Dijkstra algorithm. And if now the shortest path between destination and source is smaller than target, then I just return empty vector directly. Otherwise, if they are equal, then I go to construct the result. Like if it's mutable, I just assign the maximum possible length to the edge to the mutable edge, and then return result directly. Otherwise, it's the third case. Then here I just copy the each node's shortest path length with the destination into this array, and I run the Dijkstra again with mutable edges weight as 1, and the south now is south vertex. And also I check, if it's if current destinations shortest path length with the south vertex is bigger than target, is return empty. Otherwise, I record all of the mutable edges into this side. Here is the path, right? So it's the path from the south to target to destination with mutable edges as 1. So here I just construct a light path into this vector. And I record the worked value. I already go with the current smallest path, shortest path. And I go to check whether node, this is current node, whether current node not equal with destination. If not equal, then I get the next node on the path. And I go to check whether this is a mutable edge. If it's a mutable edge, I go to check whether the next nodes, the shortest passes length with destination is infinite. If it is infinite, I just set the current mutable edge weight as 1. Otherwise, I set the current mutable edges weight as target minus worked minus the next nodes shortest passes length. And if this value is minus, I just set the current mutable edges as 1. Otherwise, I use this value as the current mutable edges weight, and also update worked value here, and then update the node to be the next node, and also update position, and so on. So with this val, I construct all of the mutable edges weight on the current shortest path from south to destination. And here I go to construct the final result. I go to check whether this is a mutable edge. If it is, then I just check whether this mutable edge is on the existing shortest path. If they are on the current shortest path, I just use the value I calculated in this val to set this mutable edge weight. Otherwise, I set this mutable edge weight to be the maximum possible length. So in this case, it doesn't impair the current path to be the shortest path, right? So, and just return the final result. Okay, so this is the code for the final problem. If you have any questions about any problems in this computation, you can leave comments on the leave comments below. Thank you.